All right, so welcome back to the concrete workshop after the week 7 break. So today we're going to continue our discussion on Flexure, and we're going to talk about how to design flexural members. I didn't quite finish everything I wanted to say about Flexure last workshop, so I'll give you kind of a recap. I know it's probably a little too late because your assignment was already due about how to find ultimate flexural capacity, but I think it's still useful for me to kind of give a recap on that. And then in the second half of the workshop, I'll be talking about shear failure, which I'll discuss more in the second half. So to give you a bit of a recap of what we're talking about, I'll just draw like a generic flexural member. So this will be like a beam of some sort. You might see tensile reinforcement like so, which we denote with AST. And we've got the 3 stages. We've got the uncracked stage, where you might expect a neutral axis, which is somewhere around here. So this is basically saying that all of the concrete is working in flexure, and you've got the steel, and so the neutral axis or the bending axis is dragged below the middle somewhere. And then if I copy that, it's if we're looking at stage 2, what happens is the concrete cracks in regions of tension. So everything below here is ineffective. So you're really just looking at this part of the concrete that's working in flexure, as well as the steel. And then lastly, we've got stage 3, which I'll just take a second to draw out. This one, the neutral axis shifts up even further, and you start to see non-linear behavior in the concrete. So the concrete's working very, very hard. If I was to draw a material curve, this is compression for concrete. And the idea is you get a material curve that looks something like this, right? For the first 2 regions, everything's contained within the elastic region. And then for stage 3, you start to see the concrete working in compression, working non-linearly in compression. So it starts to reach this part of its material curve in terms of its strain. So that's in terms of like the different stages of flexure. In terms of how we actually solve the problems, so remember for the first 2 methods, we use the transform section. I'm forgetting the name for it, modular ratio. So we use the modular ratio method to turn it all into concrete. So we turn all the steel into concrete. And for this particular case that you can see here, which is, you've only got tensile steel, so that's called singly reinforced concrete, right? Basically, the idea is you're solving for depth to the neutral axis, and dn is solved linearly, right? So this is linear, no dramas. For stage 2, the concrete area itself is also going to be a function of dn, right? So you have to start to solve this quadratic. And I believe if you've got if you've got compressive steel as well, like so, you'll find that the first method, when you're trying to find dn, is still linear. And the second method is still quadratic. Okay, so whether you've got a singly reinforced case, like so at the top, or a doubly reinforced case, for stage 1 and 2, you're going to be dealing with linear or quadratic methods for solving for dn. So when I'm talking about quadratic, I mean you need to use the quadratic formula, basically, in order to solve for dn. So for the 3rd stage, if I copy this over, I'll run through this a bit more thoroughly because I didn't really have the time to do this last time. So let me just draw this in. Okay, so for the top case, you've got stage 3 ultimate flexure stage, where you have like non-linear behavior in the concrete. You're going to find that if you have singly reinforced concrete, which just means you've only got the tensile steel, dn will be linear. okay? And the way that you're going to solve it, and I'll show you in a second what this means. The way that you solve it is using force equilibrium. So that's just saying that all of the compressive forces are equal to all of the tensile forces, and the compressive force will have a, like dn is going to be embedded in the compressive force. So you're only going to have one unknown, and it's going to be a linear version of dn that you can just solve. So that's how you would find it for singly reinforced concrete. So in the case of doubly reinforced concrete, like where you've got the tensile and the compressive steel, you're going to find that when you do the force equilibrium, right? So compressive forces are equal to tensile forces, right? You're going to find that C is going to be, so there's going to be two components to C, right? There's a compressive steel and your compressive concrete, and what you'll find is that the compressive concrete will have the factor of dn in it, but the compressive steel is going to have dn squared embedded into it. So I'll explain what that means in a second. But basically, yeah, what you'll find is that you're going to need to use quadratic formula in order to solve for when you've got doubly reinforced concrete in stage 3. Okay, so that's a recap, and I probably talked a bit too quick. Like, if that made sense to you, it means that you've probably got a really good understanding of what's going on. But for the majority of you, I'm going to guess that made no fucking sense. But I'll try to break it down a bit further. Okay. So let's just talk about a doubly reinforced concrete section that we're going to analyze for the ultimate stage, so stage 3. So the cross section might look something like this, right? And the first thing we always need to do is solve for dn, okay? And we're gonna basically draw a couple of graphs next to our cross section. So I like to line it up so that on the left is your cross section. Then I draw a strain graph, okay? And then to the right of that, I'm gonna draw a stress graph. And then to the right of that, I'm going to draw a force graph, okay? So here I'm going to duplicate the stress graph, but you don't have to do this when you're actually working out. I'll tell you which one you actually got to draw. But what defines the ultimate stage is the strain, essentially, the ultimate compressive strain. So for stage 3, bending, what characterizes this is that the outermost compressive fiber of the concrete is experiencing 0.003 strain. Okay, so this is called your ultimate compressive strain of your concrete. And that's one point that you know for sure. The other point that you know for sure is the neutral axis, right? So your neutral axis is defined as where you have 0 strain. Okay. So now we've kind of got 2 points along this linear strain distribution, which we can basically do stuff with later, okay? So this neutral axis is going to extend for all of these graphs, right? Because we're going to be graphing everything versus the depth. Essentially how the concrete distribution for stress actually looks is like this, okay? So I'm drawing a parabola, okay? And past this point, the concrete's in tension, and we know that we're going to assume it doesn't have any tension strength, and so it's just going to break. So everything that you see here for the stress is like a parabolic, non-linear kind of stress distribution for the concrete, right? And it's going to match up with this, essentially. So this kind of parabola shape is this, but just sideways, okay? Yeah, the other thing is that FC is over here somewhere. Okay, so FC, the characteristic compressive strain, is the peak of that parabola. So it's the strongest point of the concrete. But we know that it doesn't, like for example, this point down here is going to be 0, and then this point over here is something else. So this is basically a pain in the ass to graph, essentially. And so this is a simplified method. Okay, so the simplified method in AS3600 is known as rectangular stress block. I can't spell. Just pretend to spell it right. Rectangular stress block. Okay, and this is a simplified way to say. Okay, wait. I'm gonna do one more like intermediate bit of explanation. So if you've got a simply supported beam, like so, and just pretend we have this really annoying parabolic distributed load on it, right? What the rectangular stress block is saying is instead of this parabolic function which describes our distributed load, we're going to instead pretend that it's a rectangular distributed load. And so there's kind of two things that really matter for making these two things equal, right? So we know that for a distributed load, what we're interested in is the equivalent point force. So for the one in blue behind, we know that the arrow, which represents like the equivalent force due to that distributed load, is going to be located somewhere there, and it's going to have like a magnitude of some sort, right? So the idea is that if I draw a purple arrow which overlaps exactly with the blue arrow in terms of magnitude and location, these two things are equivalent, right? So we want to find the center of that equivalent point force, and we want to find the magnitude of that equivalent point force, right? So that's what the rectangular stress block method is. It's basically saying, instead of doing this annoying parabola, we're going to instead pretend that it's, what's correct, that it's a rectangular distributed block, okay? So right now we're looking at a side-on, like a rectangle, but it's actually a rectangular prism. And I'll show you what that means in 3D in a second, okay? So how do we determine the dimensions of this rectangle, okay? So this here, we're going to call it alpha 2 multiplied by FC. So alpha 2 is a reduction factor of some sort, right? So just imagine this, for the moment, as being something like 80%, okay? So 80% of this, which let's just say this is 32 MPa, right? And then going the other way, like this way, I guess you have to imagine it like this rectangular block starts at the very outer edge, but it doesn't go down to the neutral axis exactly. It cuts off at some point, okay? So that's going to be represented by gamma. So gamma is also going to be a reduction factor of some sort. Let's just say, for the sake of argument, that's 85%, okay? And that's going to be multiplied by dn, because we know that this number is dn over here, right? So gamma is going to represent like a reduction factor for dn. So yeah. Okay. Okay. So next we have to account for the steel. So we know that we've got a steel layer over here, and we've got a steel layer over here. Okay, here and here. And there's going to be a force due to the steel here, the compressive force, and there's going to be a tensile force due to the steel here. So all of these, like, the vertical dimensions all going to be aligned for these distributions, right? And we're going to, yeah, well, first I'll just draw these arrows and I'll tell you what they mean, okay? So I'm just going to draw these arrows to represent what the steel is doing. And I'll draw one for the concrete as well. Okay, so for the steel, how we notate it on the force distribution is the tensile force due to the steel, or the tensile layer of steel. We'll call it TS, which stands for the tensile force due to steel. For the compressive steel, we call it CS. So this is the compressive steel. And CC is going to be the compressive force due to the concrete block. Okay. If we dive into the stress distribution, right? By the way, this, you don't, you can skip drawing this when you're doing your questions. Don't draw the parabolic distribution of stress because it's going to be equal to this one. So the one in green is actually what we're going to do our calculations with, just because it's easier to work with a rectangular stress block rather than a parabolic stress block, okay? So completely ignore the yellow one for now. So we're going to focus on the one in green. So the idea is the stress in the steel for tension, we're going to assume it's yielded. Okay, so if I draw a material curve, but for steel, it looks something like this, right? So pretend this represents tension and compression. Okay, so steel has the same properties for the purposes of what we're doing. In tension and compression, they're going to be the same. So this is a known point, right? And it's going to be FSY. So that's the yield strength of the steel, right? And yeah, the idea is the tensile steel is going to be assumed to be yielded, okay? And the strain limit which causes it to yield, we're going to call that epsilon SY, okay? All right, so that's all very theoretical right now, but the idea is we're just saying that the stress in the tensile steel has reached yielding. So the tensile steel might actually, in reality, be strained to this point over here, okay? For this arrow, which it's going to be kind of difficult to write stuff next to it without it overcrowding. Okay. This one is actually not going to be yielded, okay? It's going to be, we're going to notate it with sigma SC. So the idea is that the strain of the compressive steel, actually I might as well just draw out this material curve. So this way we'll call this tension. This way we're going to call that compression, okay? But it's going to be mirrored, so the material properties are the same. But the idea is that the compressive steel is actually here somewhere, okay? So it hasn't reached this point here, FSY. It's only reached sigma SC, okay? So this might trip you out, right? But the idea is this is actually how the material curve is overlaid. Boom. So it's like that. Does that kind of make sense? It's probably more confusing than helpful. Okay, so, okay, if that made no sense, just ignore what I said just now, and if you rewatch this recording in week 10, maybe that'll make sense. Okay, so, yeah, anyway, the idea is this one's not yielded, this one's yielded, but this one is now going to be kind of difficult to calculate because we know that force is equal to stress times area, right? So the idea is overall we want to compute all these like forces, right? Okay, so the stress in the tensile steel, there's actually a lot of theory. I didn't expect this to go on for so long. This first bit, one sec. I'm going to move this down for a second. Okay, so how do we compute all of these forces, right? Force magnitudes. The easiest one is going to be TS. Okay, so TS is the tensile steel. So we want to multiply by the stress. So we want to multiply the stress by the area. Okay, so the stress is going to be FSY. The area is going to be the area of the tensile steel. Okay, no dramas whatsoever. The next easiest one is going to be the compressive concrete block. Okay, so I'm going to delete all this shit. Okay, so the compressive concrete block, right? In reality, so I'm going to draw this stress distribution, but I'm going to draw it kind of from a perspective view. This might trip you out, okay, if you haven't seen it before. So this is your beam, and I'm just cut a cross section of it, okay? Boom, 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 okay? And your neutral axis might be like here. Okay, the concrete compressive block that we're looking for looks like this. Boom, like that, okay? So the dimensions this way is going to be so alpha 2 F dash C. The dimensions this way is going to be gamma dn, okay? Now the last dimension, in order to make this the area, okay, is going to be this way. So that's the width, so we can call that B. So that's the beam width, okay? So we want the overall force due to this stress block. So we need this area, okay? So we're going to multiply all of these together. Okay, so let me just highlight it in case this makes no sense. So in green over here is this one. In yellow is this one. And the one that you can't see on this 2D representation is, let's do it in, far out, zoom purple or something, is B. Okay, so B is the dimension going that way. Okay. All right, so again, all we do is stress times area, okay? So it's a stress block because the stress is going to be that, okay? So stress, this bracket, is alpha 2 F dash C, okay? And now the area is going to be width times height, right? So width is B, height is gamma dn, okay? So that's an area, that's your stress, okay? So in terms of unknowns, we've actually only got dn because the idea is AS3600 gives you these two values, right? Alpha 2 and gamma, okay? So like, for example, if you've got 32 MPa, yep. So if you've got 32 MPa, this is the formula, and you just chuck in 32, and you can compute that gamma is like 0.89, for example, and alpha 2 is 0.8, for example. Okay, so when I say 0.8, that just means like 80%, and then this one means like 89%. Kind of makes sense. Okay, so these are known basically. So you're given this, you can compute these, and you're given this, which is the width of the concrete rectangle. The only one that's unknown is dn. Okay, so one step more. Actually, wait. Before I like talk for too long, I know some people have no clue what's going on right now. Do you guys have any questions? I'm sure you have questions, but you might not be at the stage where you know what questions to ask, but that's fine. Let me just show you this, and I can come around during the break and then explain a bit more if you need. Okay, so CS is the last one, right? So this force, this is the force due to the compressive steel. So stress times area, right? In theory, this is quite simple because it's just going to be similar to this one, right? Except instead of FSY, right? Instead of FSY, we just have sigma CS, and instead of AST, we have ASC. So simple enough, right? The problem is this is not a straightforward calculation. So the idea is, oh, I already deleted the material curve for steel. Okay, so we know that the elastic modulus of steel is equal to sigma SC over, sorry, let me restate that. So stress over strain, right? That's elastic modulus, right? Okay, this makes more sense if I draw a material curve, okay? So I'm going to redraw that material curve for steel. Okay, let's just say we know this point and we know this point. So this is FSY, this is epsilon SY, okay? The steel yield point. We also know the elastic modulus, right? Okay, so if we wanted to solve for epsilon SY, you would multiply epsilon SY onto the left-hand side and then divide by ES, right? So this is actually not too bad to do because what you do is 500 MPa over 200,000, right? So it gives you 0.0025, right? So this is actually a known point, 0.0025, assuming that's your steel yield strength, okay? All right, so yeah, that's epsilon SY. However, how do we get sigma SC? So sigma SC might be here, for example, right? So this is sigma SC, right? We don't know what that is. And we can say that, let me delete this one. This point here, let's call this epsilon SC. Okay, so epsilon SC is here. This is epsilon SC. Okay, so we can find this through similar triangles. So this triangle has the same slope as this triangle. Okay, so we know what this ratio is, right? So the idea is we know this ratio. Oh, no, okay. All right. How do I explain this? All right. Anyway, point is this is equal to. Okay, wait. Give me 1 sec. Okay, so epsilon s is equal to sigma cs over epsilon sc. Oh, fuck. Okay, I keep changing the order, but you kind of get what I'm saying, right? We want to solve for this one, right? So in order to do that, we rearrange and we get this. Okay. So this now just becomes epsilon s, ES times epsilon sc, all right? And we know what this is, okay? Now the difficult part is trying to find this now, okay? So bear with me, guys. I'll give you a break after this. I know we haven't done any like actual questions, but I'll give you a break because your brain probably hurts, okay? So just bear with me, just stay with me, all right? So we want this number, right? We know what this number is, and we know what these depths are. So that's dn, and let's just say that is dsc, so the depth to the compressive steel from the top. Okay, so similar triangles, right? This triangle slope is equal to this triangle slope, so rise over run is equal to rise over run, right? So let's make it more obvious. So the smaller triangle, right? Let's say the rise is epsilon sc. The run is here to here, right? We know what this dimension is, and we know what this dimension is, and so therefore this dimension is going to be the difference between dn and dsc. Okay. So we want this dimension here. So that's dn minus dsc, okay? And then this bigger triangle, right, rise over run, we know what the rise is 0.003, and the run is dn, okay? All right, now we're cooking, right? So yeah, well, what we do is we're gonna rearrange for epsilon sc. So epsilon sc, we cross multiply, right? So let's put dn on this side. 0.003 dn minus dsc. Okay, so all I've done is cross multiplied, and now I divide both sides by dn. So I get all this shit over dn. Okay, so you can see there's going to be two dn's, right, which is going to result in a quadratic later, which is what I was trying to say earlier. Okay, so this monstrosity is what we plug into this. So this whole thing gets striked out and becomes that. Okay, I know like, you know how like lecturers spend a lot of time like deriving fucking equations, and you're like, what? Like, just give me the final answer, bro. Like, you know what I'm saying? Like, but this is a course where you have to derive it yourself for every cross section. So this process is actually very important, right? That's why I'm spending so long telling you about it. Okay, like that's the difficult thing, right? So, yeah, okay. I didn't mean to scare you. I'm sorry. What I'm trying to say is learn how to do the questions for when you don't have compressive steel, right? When you don't have compressive steel, life is easy because the tensile steel is always yielded, okay? But when you have compressive steel for stage 3, so stage 3 flexure, your life becomes very hard, okay? That's what I'm trying to say. dn becomes a quadratic, and you have to derive it yourself, okay? In terms of how to solve for dn as a quadratic. Okay, so yeah, everyone's really sad, so I'll give you a break. So we'll come back at sorry, I'll give you a shorter 47. All right, we're gonna go to a 47, 147.
It's like very simple.
We do a random round for those. Here you go. It's a 3D printed slab and beam
Oh my god.
Actually, wait. Let me pick.
Can you share the design? What you I think
All right, guys. The winners for the sorry. The winners for the 3D printed slab and beam system. Actually, it was 67.
Oh!
38, 11, 19, 20, 5 and 6. So come out, come to the middle, and I'll grab the beams for you.
What? Am I budgeting on that? It was the first one as well.
Yeah. So instead of me coming to you, can you come to me, please? All right. Sorry. Listen up. All right. Instead of you guys coming to me. Oh, sorry. Other way around. Wait. Listen up. Guys. Quiet down. Okay. So instead of me going to all of you guys, can you please come up? So 67, 19, 5, 6, 20, 11, and 38. You go, mate.
Thank you.
No problem.
Thank you so much.
Oh, actual? Oh shit, let's go, right? No problem. Here you go.
What am I going to do with it?
Here you go. I think one person was missing, but you can get it at the end of the class. Okay.
I'm going to do the test outside.
So, all right, let's continue with the workshop now. Guys, shut up. The fun's over. All right, we're here to learn. All right. I'm kidding. Okay, so what I'm gonna do? Actually, no. Yeah, sorry. You can keep talking for a sec. Okay. Manesh, can you close the light, please? Yeah, it just does that. All right, we're gonna kind of run through this concurrently, right? Concurrently? In parallel. Okay, so I want you to pay attention to the screen on the left for now, and then we're gonna use the screen on the right as like supplement to doing our questions, all right? So, all right. So to give you a recap of where we're at in this course, week 5 was Flexure, which, by the way, that's where all that theory came from that I was talking about before. So that was kind of week 5 stuff. It was quite a lot to take in, but just rest assured, that's the hardest that the course gets. Okay, so if you understand that whole spiel that I was talking about earlier right now, then you've got a really good grasp of what's going on. But you get opportunities later in the course, like when we're talking about columns in week 10, to catch up and relearn it, because it's going to be reapplied to week 10's topic, columns. For now, we have to shift our thinking a little bit away from finding the capacity of a flexural member to how to design a flexural member. And how we design it is going to feel a little bit different, even though ultimately it is building off the same theory. What we do in designing members is a lot of guess and check work. It's going to feel very strange to you guys because you're probably not used to. You're probably used to plugging a number into an equation, then like it spits out it does some maths, and then it spits out a number for you. But the further you get into your degree, the more you realize that a lot of engineering design is about like iterations and how to guess and then improve your design. So that's essentially what flexural design is about. And then we'll also be talking about shear a little bit this week, which we'll talk about shear design, same concept. The shear design next week, okay? So let's talk about designing flexural members first. There's kind of 2 types of questions that you'll see if you look through the workshop questions for week 7. The first type is when your concrete shape is known and they want you to design the steel, okay? So for example, the scenario you can see on the right, that's when your loads are given and we've got set boundaries of what your beam's cross section can be. So it tells you what the width is, and it tells you what the depth of that beam is. But what it wants you to do is find the amount of steel to put in. So that's one type of question. That's where you're designing the reinforcement, quote unquote. The second case is where you're given the loads, but you're actually not given the depth or the width. Okay, and then you also have to find the reinforcement. So you can see there's going to be a lot of moving parts, and the reason why we have to do a lot of guess and check work is there's actually so many moving parameters that we need to essentially have like rules of thumb that we go off of in order to tell us what the depth is going to be and the width, etc. So those are the two types of questions. And in the example that I run through, I'm going to go through case 2, because case 2 is basically a longer version of case 1. Okay, so where a lot of these guess and check numbers come from, so the initial guesses, is from this textbook called Reinforced Concrete Basics, which I briefly mentioned in week 5. And there's a section in it, right, in the appendix, which is called Recommendations for Preliminary Sizing of Concrete Members. So that's where these tables that you will see come from. So in this course, we're going to be specifically talking about how to design the beams, even though we're dealing with a slab and beam system, like the ones that you saw, like the little model things that I put on your table. We're actually designing the beams, right, even though it's connected to the slab. Okay, so yeah, there's going to be guess numbers, and I'll tell you how that works once we see the question. There's going to be all these steps, okay, but it makes more sense. Like these won't really mean anything to you on your own, on their own. What matters is how you apply them in a question. So I'm just scrolling through them quickly now because that's actually what I'm going to get up on the screen on the right. And we're going to be, so what you'll see, right, is you're going to see two projectors, right? The one on the left is my working out that we're going to go through a question with. And then the one on the right is going to be kind of our little recipe book, I guess, of steps, okay? So you're going to see all this crap. You're going to see all this crap, and we just have to follow every step, okay? Okay, so here's the question. Right? Oh, does this look familiar to you? So this is a 3D model thing that I modeled up in Blender. But I hope it kind of illustrates to you how the loading will work when we run through the question. Okay, so let's read the question first, just so we're all on the same page. So it says, a reinforced concrete slab and beam floor system has a slab with a depth of 180 millimeters, okay? So that's referring to the thickness here of the slab. It's supported by T-beams at 6 meter centers. So this purple shape that you can see here is a T-beam. And a T-beam is basically a beam, like a rectangular beam. But since it's connected to the slab on either side, it picks up a bit of the slab strength. Okay, so therefore you get a resulting T-shape. 6 meters centers is referring to the fact that the middle of this beam and the middle of this beam is 6 meters apart. The beams are simply supported over a span of 8 meters, right? So now when we're saying that there's a span of 8 meters, we're not referring to this angle anymore. We're referring to the other angle. So viewing it from this way. So if my eye is there, I'm pointing that way. So here you can see it's simply supported. And the overall distance, right? So the net distance between the edge of that column and the edge of this column is 8 meters, right? So the clear span. But take a flexural span of 7.4 meters, okay? So a flexural span of 7.4 meters, this refers to the fact that, look, in a perfectly, give me 1 sec. Keep pressing before. Okay, so in a perfectly simply supported system, right, we know that the bending moment diagram looks something like that, right? If we have fixed supports, right? Oh, sorry, and I should mention this is for uniformly distributed loads, right? If we have fixed supports, we might have a bending moment diagram that looks like that, something like that, right? So you've got negative moment at the supports. but in a lot of real life systems, we have something that is in between a pin and a fixed support, and we call that, and we represent it like this, we call that a rotational spring support. Okay, so this is supposed to be like a spring, but it's like a coil, right? So wrapped around. So this basically, yeah, if I just draw this as like the beam, the bending moment will be somewhere in between those two cases, okay? So this is a rotational spring, and it represents a range of possible amounts of rotational stiffness, right? So if it's fully loose, right, and it's fully able to rotate about this hinge of the pin, the spring might have a value of 0, right? The spring might have a rotational stiffness of 0, whereas this one will have a high rotational stiffness value, right? That's the idea. So anyway, so in reality, we have something like this. All that we really care about is what is this distance between points of contraflexure. So contraflexure just means when your bending moment diagram switches between positive and negative bending. Contraflexure just means you've got 0 bending, 0 BMD at that point, and 0 BMD at that point, okay? So yeah, the question tells you already what that distance is, and that's called A. So that's the flexural span. Okay. All right. The floor is to carry a live load of 3 kPa. Okay. So this is a pressure value, so Q. Yeah, I'll just keep it as Q because that just means live load as well. And the dead load, let's represent that as lowercase g. Okay. So that's dead load as a kPa value. kPa. kPa. Okay. Yeah, and then design the longitudinal reinforcement at the midspan of the beam. That's what our goal is, and it gives you a bunch of I guess like values that you'll need in the question. Yeah, in the question. Yeah. Okay, so we have all those things as well. Okay, so the first thing you kind of have to realize is the idea of tributary width. So if you think about it, right, basically we've got 6 meters between this column and this column, right? And between the beams as well. So that's going to be true on both sides, okay? I should probably use a different color so it's easier to see that number. So that's 6 meters and that's 6 meters. So the way that forces flow is very similar to, I guess, like electricity, where it wants to go to the path of least resistance, okay? So if there is a bit of weight, let's say here, we're going to just pretend that like a magnet, it gets attracted to the beam that's closest to it, okay? And then similar for like a point over here, the weight gets attracted to the beam that's closest to it. So the idea is the tributary width or the tributary area represents this area basically. Which portion of the floor is absorbed by the beam? Does that make sense? Okay, so that's tributary area. So for this beam, we're going to say half of it on both sides is going to flow. So it's going to be flow into the beam. So it's going to be 3 meters and 3 meters, right? So if you add up both sides, it's 6 meters, okay? So it just happens to be that the spacing between the beams is also equal to its tributary area, because if you add up these two, okay? So that's where 6 meters comes from, which you'll see in a bit. Okay, so now I've got all the steps and stuff lined up. Which so you can follow my working out on the left screen, and on the right screen, let me zoom in a little bit. I'm gonna have all the steps. Okay, so this is from my little like cookbook. All right. So step 1 is the preliminary depth. Right. We're dealing with we're trying to design the beam. Okay, so that we're designing the T-beam. So we're looking at this table at the top here. All right, which is what I've included here. Okay, so in order to basically one sec. Oh yeah. So yeah, like we have an input that we want to put into this table so that we can get an output, right? We have a few inputs, I guess. The first one is that we have a simply supported system. So simply supported means we've only got 2 supports, right? Total deflection. This will make more sense next week when we start talking about deflection, but just read this part of the table for now. And the idea is they give you trial values based on whether you've got medium or high loading. So our loading is in the ballpark of 3 kPa, right? And then there'll be self-weight as well. So it's closer to 2 than it is to 6. So we're going to read off the column which says 2, which is just describing what a good guess would be, what a good initial guess would be for kind of like a medium loading, okay? All right, so now that we know which formula we're going to use from this table, right, and this whole table is for determining the depth, okay? So we're going to guess an initial depth of ln divided by 10. So ln, remember, is the clear width, right? Oh, sorry, the clear span. So what we'll do is we'll convert that 8 meters to millimeters and divide it by 10, which gives us 800 mil. So 800 is going to be our beam's depth, okay? So that dimension there is going to be 800, right? So I haven't drawn the T part yet, okay? All right, step 2 is as like a fraction of the depth is going to be our width, okay? So if I scroll down on my cookbook, right, you can basically guess a range of numbers, right? So what you would do is, this is based on aspect ratio, right? So when I say aspect ratio, what I'm saying is, imagine these two rectangles, right? These two gray rectangles represent the same area, okay? And we know what D is already. It's going to be 800. So whether your width wants to be, so if your width is 0.5 D, that means it has a 2-to-1 aspect ratio between depth and width. If your aspect ratio is B is equal to 0.8 D, that means that it's going to be 80% of your depth. Your width is going to be 80% of your depth, okay? What we're going to do is, in our question, we're going to guess 0.7. So this means that we're going to assume that the width is 70% of the depth, okay? So once we plug that in, we get 560. So looking back on a little diagram, that's saying that we're going to guess the concrete's beam's width is 560, the rectangular portion. Okay, cool. That's the second step. Third step, we want to find our loading and max bending moment. Okay, so this is going to require finding the unfactored loads first before finding the factored load, okay? So we know that in the question, it says we are going to take the self-weight as the only dead load. So we're not going to take any superimposed dead loads. We're just going to take it as self-weight. So the self-weight formula is going to be your unit weight, right, which is 25, right, given in the question, multiplied by the area, okay? So you might be inclined to think that the area we're interested in is going to be some portion of the T-beam's flange, right, which is what we're going to take for its capacity later, right, as well as the rectangular portion, like the beam itself, the web. However, that's going to not be conservative enough. What we need to do is we need to, when we're calculating the self-weight, we need to pretend that it's the entire tributary width, okay, for the flange. So what I mean is, if I look back at this diagram, instead of taking this little T-beam's width when we're calculating the self-weight, we're going to literally take it from here, the middle of where the load is attracted from, all the way to the middle. So this entire area is actually going to be what we calculate our self-weight as, okay? Otherwise, some of the self-weight might not be accounted for, which is no good. Okay, so let's draw out what we know about this beam's dimensions, right? We know the slab was 180 mil because we were given it. We know the overall depth is 800 because that was our guess based on the guessing formulas. And we know that the web width, which is the width of just the rectangular portion of the beam, is 560. So we want to find the area, which is what I've highlighted in green, okay? And so that area Okay, well, I actually just did it on my calculator, but I didn't write it down. But you just try to find this area, like that. Okay, and then you multiply that area. Sorry, and what you're going to do is you have to make sure that area is in meters squared, because all these dimensions that you see right now are in millimeters, right? So if you do it in meters, and you multiply it by the unit weight, which is in kilonewtons per meter cubed, you'll get the answer in the correct units, which is kilonewtons per meter. Okay, so we get a WG of 35.68. Okay, so that's the linear self-weight. So when I say linear self-weight, again, this is where it's really useful to have a diagram from the 3 model thing that I did. Linear self-weight or linear load looks like this, okay? So we're just focusing on the beam part, right? We've turned this kind of like 2D pressure into a 1D line load, okay, which runs over the beam. We're going to do a similar thing for Q, right? So we were told that lowercase q, right, is 3 kilonewtons per meter squared. So that's 3 kPa. So this is the same thing as saying kPa. And we're going to multiply that by 6 meters, okay? So 6 meters is the beam to beam spacing. So remember, that's just the same as saying that's kind of the width which the beam like draws the forces in like a magnet from the slab, right? And since we originally had a 2D pressure like that, we're just converting it into that line load, okay? We're turning it into a 1D loading like that, okay? Okay, so we get 18 kilonewtons per meter. So that's our linear live load. Make sense so far? Thank you, Andy. I know you've already done this course, but thank you for nodding anyway. Okay, so once we crunch these numbers, so what we're doing here is this is the dead plus live load. So that's G, that's Q. Let's do WG, WQ, and this is WG. So this first one is our live and dead load. Sorry, I should say the other way around. The dead and live load load combination, and the bottom one is just the dead load load combination. And so once we compute this, we get these two numbers, right? Which I'm not going to say out loud. And you see that the top one is larger. Okay, so we take the maximum of it because that's the one that governs. Okay, so now we've got our factored. Yep, Alex.
With the dead load, is there ever a situation where just the dead load is greater than the dead and live load option?
Yeah, that's a very good question. Very good, very good. Okay, so I guess one thing you have to consider is that loads will have different shapes. So I'll give you an example. So you've got a beam, and you might have a UDL, and you might also have point loads, right? So this is why when we're finding the bending moment, you can't directly add, say like WG and like say the point load was a live load. You can't like add these directly together because they have different shapes, right? But let's just say for the sake of argument that you've got a simply supported beam and you've got a uniformly distributed load, and that represents both the shape of the dead load and the live load. Okay, so if you play around with these load combinations, right? I'll just write it like this. If you play around with this load combination and this one, okay, what value of G and Q will make it so that the dead load only will govern? Okay, so let's just say that live load, let's keep that as at 1 kilonewton, okay? The cutoff point is once the dead load's 10 times bigger than the live load. Okay, you can try this yourself. You'll find that these two numbers will be equal in this case. And if this is higher, let's say this is 11 kilonewtons, the dead load will govern. The dead load only case will govern. Okay, but I would say generally it's pretty rare that the dead load only case governs. I've only had this come up in like a work setting before when there was a brick wall that was like several stories high that we considered as dead load, and that was the only case that I've ever seen it governed. So yeah. Anyway, it's usually live and dead load governed. Okay. So sorry, where were we? Okay. So we're calculating the bending moment, right? So what we want to do is we know this number now. Okay, we can plug that in. And what you can see here, this is like a preset formula for like a simply supported beam's maximum bending moment. Okay, so just going back to this diagram, sorry. Let me just. So this is simply supported beam, and if you have a uniformly distributed load, okay, if this is L and this is W, to find the maximum moment, right? This M is equal to WL squared on 8. That is a preset like formula, okay? And you can work it out yourself if you do your static analysis methods, but this is like a preset formula. For our case, it's a little bit different because we're considering these as like rotational springs or coils or whatever. And so we've got a bending moment diagram that looks more like this, okay? What we say is that approximately for this flexural span, to get the maximum bending moment, right, you would do this. So the only thing that changes is instead of L, you take the flexural span A, okay? And then you're gonna get the bending moment, the max bending moment, okay? Does that make sense? Kind of. So that's the formula that we're gonna use, all right? All right. So that gives you 478 kilonewton meters, which we're going to multiply by 10 to the 6 later to get it in Newton millimeters. All right, so on the right-hand side, I'm going to scroll down. Yeah, you can see kind of the notes that I was writing. And now we're up to step 4, where we're going to refine the concrete shape. Okay, so we're going to make a few assumptions, right? We're going to assume that the ductility constant Ku is 0.25. So keep in mind that in order for something to be considered ductile, it needs to be less than or equal to 0.36, right? So we're going to assume a ductility well below that, because once we design our beam, the goal is that it's going to be ductile. So it will stay under this number, okay? Because there's going to be a lot of like back and forth iterations, right? So we want to kind of set it well below this threshold. And then in a similar way, we're going to assume a phi factor or a capacity reduction factor of 0.85. And this is because if this number is exceeded, rather, if this number stays under 0.36, then you can have a capacity reduction factor of 0.85, okay? The other thing we're going to do at this stage is now make the width we're gonna change the aspect ratio a little bit. Okay, so in our initial guess, we had an aspect ratio that looked more like that. Okay, so that width was 0.7D. Now we're gonna change it to a slimmer one, and that's because these slimmer beams are more materially efficient. Okay, if you think about this formula, right? The more depth you have, like the depth is to the power of 3 times more effective in giving you flexural stiffness than the width is, right? And so therefore, if you have a slimmer beam, the concrete is behaving in a more efficient way to resist flexure, I guess. Hopefully that kind of makes sense. Okay, so the other thing we do, so this is the formula that we're going to use, right? But the other thing we do is we're going to pre-bake our gamma and alpha 2 values, right? Which are our reduction factors for the compressive concrete block. So we're going to replace F-C in these formulas by 32 and just pre-bake these like so. So now when we're given this formula, we can basically just turn it into a function of only D, lowercase d. Okay. Oh, sorry. The other thing I should mention. Okay. Sorry, my bad. We don't quite do what I was saying here. We're actually doing this. So d, lowercase d, is the depth to the tensile steel, right? So anyway, point is, kind of ignore what I was saying earlier. The idea is we're just gonna assume a flat, the width to effective depth ratio is gonna be 0.5 rather than width to total depth, okay? Sorry, so anyway, we're gonna replace that with 0.5 lowercase d. We're going to replace this with the bending moment, which we calculated earlier, and we're going to multiply it by 10 to the 6, and that's going to convert it to Newton millimeters. The phi factor is going to be 0.85. The alpha 2 value is going to be 0.8. F dash C is going to be 32. Gamma is going to be 0.89. Ku is going to be 0.25. Gamma Ku is going to be 0.89 multiplied by 0.25. So this is all just plugging into formulas, right? And what you're going to find is that on the left-hand side, right, this is going to become 0.5 d cubed, right? You're going to multiply both sides by 2 in order to, so I'll do 2 on this side, and then this will get rid of the 0.5. Okay, so you're going to have all this in terms of d cubed, right? You're going to cube root both sides, and then you're going to be able to get a value, an inequality for just d, lowercase d. So that's what this is, okay? And I couldn't be fucked to write it all out. So you basically do all that stuff on your calculator, okay? And then you cube root it, right? So you do all this, you cube root it, and then you're going to get d is greater than or equal to 605, okay? So, yeah.
That formula, does that come from the concrete textbook? That's not
it's so a concrete textbook like the, yeah. You're talking about, fuck, where was it? This one, right? Yeah, it'll be on there. It's just rearranged formulas from the standards, though. So it all comes from the standards, but they kind of just nicely present to you how you would use the standards to design with, I guess. Sorry, I'm trying to find the right page. Give me 1 sec. Okay, cool. So yeah, so just to recap, we're here now. So we're saying that the depth to the tensile steel has to be, and sorry, this is for a T-beam. This has to be at least 605, right? So it has to be greater than 605, greater than or equal to 605. So we're gonna do that, and then we're gonna replace this with 605. But we actually want it in terms of d, so we're actually more interested in this value, okay? So this is large uppercase D. So we're going to have an assumed axis distance of 65. So that's saying that the cover to the middle of the bar is going to be assumed to be 65 based on various durability requirements. And I'll give you this. And when we want to round it up, okay. Sorry, let me scroll down on the cookbook, okay. When we round it up, we want to round the value up to the nearest 50 mil. Okay, so it goes up to 700. Okay, so now this is going to become 700 because remember this was a minimum value, right? So this has to be greater than 605. So we're going to choose 700. Okay, so now this is, instead of a range, this is going to become an invalid. Sorry, we want this as a set number rather than as a range, right? So what we do is we go back to 700. And then subtract the axis distance back off, which I have to turn my page for, giving us 605. So now we have like an actual established dimension, I believe. Is that what I did? Yes, 605. Okay. Wait, 700 minus, that's not right. What the hell? Oh, okay. Anyway, whatever. do 700 minus 65 in your calculator. I can't be fucked to do that right now. Okay, whatever. Fine, I'll do it. Okay. So, oh man, I did this wrong. Okay, whatever. So this is now replaced by our new number. Okay, and what we do is we go back to this sizing formula, right? Let me scroll down on the cookbook, right? We go back to the sizing formula, but we actually want to rearrange it for the concrete width, right? So, yeah, when you move all this to the right-hand side, now it's going to be BW is greater than 275. We want to round this up generously, okay? So this is going to go to 350. Okay, so the reason for this in this particular question, it comes more from like a reinforcement detailing step later. Okay, so if you imagine a T-beam like so, we're choosing this dimension, right? We're choosing 350. However, like when we choose the reinforcement, let's just say we pick 3 bars of tensile reinforcement. Think about how much space we actually have in between the bars, okay? So when your steel gets too congested, there's gonna be problems with, like, imagine they're pouring it on site. There could be like rocks or aggregate from the concrete mix that gets stuck between the bars if there's not enough space between the bars. So the reason why this has to be 350 is there needs to be enough space between the bars to, yeah, have your concrete poured correctly. Okay. So, yeah, we now have to recalculate the dead load, right? The reason is because when we were calculating the dead load earlier, we didn't actually know everything about this beam. Like, for example, we've now changed what D is, and we've now changed what the web width is, right? So now we have to recalculate the self-weight because these dimensions of the beam have changed, right? One sec. So now that we have fixed dimensions, right, we can do this, right? So area multiplied by unit weight of the concrete gives us WG, okay? WQ doesn't change because we didn't do anything which changed the live load or how it's applied. And we're going to do this whole load combinations thing again, right, to find the factored distributed load, which gives us this, okay? So now this is W star. And then W star can be plugged into this formula, right? The flexural span didn't change, okay? And that gives us 444 kilonewton meters, okay? So I'll give you a few seconds to copy that down if you... Okay. So now, our next step in our cookbook is the initial steel sizing. So all we've done so far is the concrete, okay? We still have to do the steel. We've just chosen the concrete's dimensions, right? Okay. So here's the formula for sizing the steel. Okay, this is the initial sizing formula for the steel. So we actually know the bending moment for sure now. Okay, so we can plug that in. And we have a ductile section. So the reduction factor is 0.85. We have 500 MPa steel. This is all wrong. Fuck. Okay, sorry. D is, it should be 635. Okay. I think in my numbers I might have done 605. Okay, sorry. So just recalculate, just check what I've written is actually correct or not. In terms of, yeah, anyway. So these numbers will be slightly off because I would have written 605 instead of 635. But just focus on the process, okay? All right, so the last thing is this rectangular purple box. So if you look at, and just for the sake of the video, I'm gonna just change, I'm just gonna scroll up to it as well, because this is kind of important. Far out. Okay, so when I have a purple box like this, it's gonna basically mean you have 3 different cases, right? If you have a rectangular section, you'll choose this case. If you have a T-beam, you'll choose this or this, depending on whether we're referring to the T-beam, whether we're designing the steel for the T-beam at the support or the midspan. So the question tells us to design the T-beam at the midspan, right? And so that's what we're going to have to do. And so we're going to choose 0.95. So this has to be 0.95, right? Okay, so now when we compute this, we get this, right? 1,732 millimeters squared. Okay, so all this is saying is this isn't actually going to be the steel that, like, this isn't the amount of area of steel we select. All we're doing is finding a range of values which are acceptable right now for the area of steel. So the steel that we select has to be greater than this number. Okay, but it will, yeah, we just need to roll with this number for now. Okay, so this is a range of numbers, but our threshold number we're going to plug into this equation, right? So what we're doing in step 6 is finding the depth of the compressive concrete as if we had this value for steel. So we know all these things that I've ticked. We just have to calculate BEF. Okay, so what is BEF? In a T-beam, BEF is this. It's the width of the flange, the effective width of the flange. So the idea is that the T-beam picks up a little bit of strength from, or just like the rectangular beam, picks up a bit of strength from either side due to the slab kind of being attached to it, okay? So this is actually the slab, but the beam itself, instead of just having the strength of the rectangle, it has a bit of strength being contributed on both sides due to that slab, okay? And the formula follows this, okay? So it's going to be BW. Wait, let me just go to the next page of my notes. It's going to be BW, which we've established is 350, plus 0.2A. Conservatively, they've done it as L. I guess not conservatively. It would be beneficial to do it. It would be like unconservative. But in the solutions to this question, they've decided to do it as L. Okay, I would have done it as 7,400 personally. But yeah, okay. And then, so BF becomes 1950 millimeters. Okay, so that's 1950 millimeters. That's what we plug in to find the depth of the compressive concrete, okay? So scrolling down on my cookbook and following the associated step, we've got this, okay? Now we have a more refined steel sizing. So before we had an initial steel sizing, now we have a different formula which tells us a more refined steel sizing based on the compressive concrete depth, okay? So this value, right, is what we plug in from here, okay? And when we plug everything else in, we get this number. And so what this is telling us is that the range of steel which is acceptable has to be greater than 1668, okay? So when we look at our design area for reinforcing bars, right, when we look at the nominal areas, we can think of it in terms of two things, right? The bar size as well as the number of bars. Okay, so two which are greater than this number but still appropriately sized would be, for example, 4 N24s. So that's one option. So this here would be 4 N24s. The other option is 3 N28. Okay, and to be honest, you can pick either, but there's one which I believe would be, I mean, it can kind of go either way, right? So remember, you got your T-beam. And remember, the width of this beam was 350 mil, right? If you decide to put 3 N28s in there, I guess, actually, I might like pass this to you guys. Why do you think that 3 N28 would be better than 4 N24s?
Yeah, more spacing, so the aggregate can flow through.
Exactly, right? So one benefit is you get better clear spacing. Okay, so more space between the bars is easier to pour the concrete, right? So the concreters will love you. Okay, so that's one consideration. Okay, but on the contrary, what if you wanted to do 4 N24s? What's the benefit of doing N24s, of rather 4 N24s? Yeah, Andy.
The tradies on site can bend it more easily than the trades.
Bending's one thing. I might have said this in my last, in my old like series of whatever, when you were learning concrete. Bending's not as important. So what Andy's referring to is here we've got, I'm going to draw a perspective view. You got a T-beam, right? These bars are going to be straight bars, right? You don't really need to bend them. And then the ones at the end with the anchorage are going to be these cogs or whatever. They might already come like bent before they get to site, right? What Andy's referring to is that in a pinch, if you've got a straight bar and you want to turn it into a bent bar because they ordered the wrong one or whatever, if you've got so if you imagine the bar cross section, right? I'm going to exaggerate it. This is N24. This is N28. If you think of the moment of inertia being a function of the diameter, the thinner one is going to be a lot, the smaller diameter one is going to be a lot easier to bend, right? So if you want to turn the bar into like a cog, for example, right? Okay, sure, but I would say that's not actually the most important thing. What is the benefit of having N24s? Yep, Manish. I kind of get what you're saying. I would say N28 actually has more surface area because if you're thinking of a N24 to N28, right? The bigger diameter has a more surface area. I think what you're thinking of is surface area divided by bar area or something like that, maybe. Yeah, okay. Still, that's not what I'm looking for. Anyone else got any other ideas?
Slightly more economical because the area of steel is less.
Oh, like these two numbers? That's true. So like if you do N24s, that's 1800 is less than 1860. Okay. Oh, I'll just give you the answer, right? Sorry. These are lighter. Okay. So from a steel fixer's perspective, they'll love you if you give them a lighter bar. Because if you try picking up an N24 versus N28, you'll notice the difference. Okay, it's going to be a lot lighter to have a smaller bar, a smaller diameter bar. Okay. Okay. Anyway, sorry. Those are all considerations, but it's good to think about these things, right? So that you're not a delusional designer. For this particular question, I've decided to go for, or I think the workshop solutions decided to go for 3 N28s. Okay, so that's the one which has this as the area of steel. Okay. So that brings us to design checks, right? So this is where you start to check for like beam spacing, bar spacing, etc. So this first one is a beam spacing check. And this one has already kind of been fulfilled for you, like based on how the question's presented to you, but it's still something you need to check as a designer. Okay, so it's basically saying this should be greater than this, okay? So what does this come from? It comes from half of the clear spacing between the beams, okay? So we've got a spacing of 6 meters. That's actually not the clear spacing, but anyway. So we've got half of that. Oh, so sorry, there it is. Yeah. That's the beam width. Okay, so if you imagine the beams like this, okay, middle to middle is 6,000, and then we want to get rid of half the beam width on either side, right? So that's 350 over 2, 350 over 2, okay? And if you add those together, obviously you just get 350. So these two things together are 350, right? So that's what we subtract off. So that's the clear spacing here, okay? We divide that by 2, right? So let's just call it x, right? This number is x. We want to make sure that x is greater than 10% of your flexural span, okay? So it basically is because this number is bigger than this number. So that's the clear beam spacing check. Okay, next is the minimum steel requirement. So we have to calculate something called alpha B, which is basically your beam strength coefficient. And if you look on the right-hand side monitor or projector, we've got 3 different cases as well for this. So it depends on if you've got a rectangular section or a T-beam at the support or a T-beam at the midspan. Here we're designing the T-beam and the steel for the midspan, right? So we're going to choose that bottom case. And so here's that formula that I nabbed from that cookbook. And we're just going to plug everything in, okay? So BEF, right, is the T-beam's flange width, okay? So 1950. BW is the web's width, right? So 350. DS is the depth of the slab. D is the overall depth, okay? And if you compute all of that, you get negative 0.15, okay? But the formula actually keeps going. The formula says that everything here has to be greater than another value, and the other value is a minimum value. Okay, so if you look at the cookbook thing on the right hand side, we've got minimum values that we need to basically have in case the maths on the left gives you a number that's too low. Okay, so it has to be greater than 0.2 multiplied by this. To the power of 1/4. So the minimum value for alpha B in our case is 0.31. Okay, so this is the value that we set it at because we don't want this value. It's too low. Okay. All right. So now we can check the steel. And so remember what we're doing is we're checking for minimum steel, right? The minimum steel formula is basically just saying that the steel area has to be greater than this number, right? So alpha B, we calculate it as 0.31. D is going to be 700. This is supposed to be 635, but I think there's a mistake in my working anyway. And then your flexural tensile strength, remember that's got an empirical formula in the standards of 0.6 square root F-C, right? F-C was 32. FSY is 500, so that's the yield strength of our steel. BW, we know that. D, this should be this number. Okay, and then all that is equal to 568. So the idea is that since this is greater than this, we're okay. So the next check we have to do is a ductility requirement check. Okay, and what we need to do is we need to calculate the depth to the neutral axis, okay? So AST, we put in our updated steel area, or our final steel area. We put in steel stress. We put in gamma, alpha 2, F-C, BW, right? And what we get is a DN value of 20.9. And so DN sits within the flange of our T-beam, right? And if you've tried to do a calculation yet with DN that's in the web, you'll know how annoying it is when it's not in the flange. So DN sits within our flange, so that's all good, right? In other words, the depth of the neutral axis is about 20.9, and the depth of the slab is 180, right? So since this is less than 180, we're good. Because if it's down here, we have to do other stuff, which is annoying. Okay. Now we check that the ductility requirement's fulfilled, and that's just a matter of taking the ratio between DN and D. Okay, so DN is 20.9, and D was this, which, again, I don't know if this number's going to be right, because it might be calculated with 605. Anyway, this number is actually exceptionally low, right? Because you kind of want it in the ballpark of 0.25-ish, or like comfortably below 0.36, except not like super low. This will lead to potential serviceability issues later, but we'll talk about that next week, or maybe the week after at this rate. Okay. Step 8D, strength check. So this is just saying that we need to make sure our beam doesn't break based on the load. So this is a final check for the strength, okay? So where this formula comes from is if you have a, okay, let's say we have a T-beam. We've got a T-beam, and we've got tensile steel and a compressive concrete block, okay? Like so. We have a moment couple. So the idea is that, I don't know if I'm over-explaining this. There's a force going in and out of the page there and there for the compressive concrete and the tensile steel. We have some kind of lever arm. So what we're doing is to find the moment capacity, where phi mu, we're doing phi multiplied by ts multiplied by that lever arm. And that's where this formula comes from, okay? So phi is that, ts is this, and the lever arm is this, okay? So we're just doing a quick calculation. So that's the case for singly reinforced concrete, okay? So let's just see how all these things plug in, okay? Like this, these are all the values like for the steel, etc., that we've worked out. 0.89 times 20.9. Okay, and that gives us a capacity of 494.7. So what you'll notice is that this number, being the capacity of our T-beam, is greater than m star. M star, remember, is the loading that we're putting on it, or the imposed bending moment, right? So because our beam is stronger than the amount of loads that we're going to put on it, we're okay. Okay, so that's what that strength check is for. Let's keep going. We've got the detail checks, okay? So the detail checks is all those things to do with spacing of bars, cover, etc. So minimum clear spacing, okay? We've got between bars. It follows this formula, okay? So we know the width is 350, the depth 700. This was 635. And n is the number of bars. So remember, we chose a beam with 3 bars, I believe. And then this is the bar diameter. Let's call it D subscript B. So we chose 3 and 28ths, right? So basically the clear spacing between the bars, right? So from here to here is 82. Okay, so now we have to check whether 82 passes 4 subchecks. Okay, it has to be greater than 25 mil. Okay, so you're just not allowed to have sorry, looking at the cookbook, so greater than 25 mil comes from the American standards. Okay, but whether you're in America, Australia, New Zealand, whatever, like the idea of having a minimum spacing is gonna be the same, right? So we take the American standards as like one type of check, right? So we say that the spacing between bars, the clear spacing between bars should be greater than 25 as a very bare minimum. It should be also greater than the bar diameter. Okay, so here we've chosen N28ths, right? So it should be also greater than the bar diameter. And then it should also be greater than 1.33 multiplied by the diameter of the largest aggregate of your concrete mix. All right, so if it's not explicitly said in the question, this should be at least 20 millimeters, okay? So, or just assume 20 millimeters if it's not given. So this is saying that the largest rock in your concrete mix is going to be 20 millimeters, which gives this number. And in the Australian standards, right, all that said is that the clear spacing should be less than 300 millimeters. Okay, so that's not very helpful, which is why we lean on these other standards like the American standards and kind of logical checks for spacing between bars, right? We want to make sure the space between bars isn't too big, but it's not too small either. Okay, any questions about that? Nope. Okay. Step 9b, minimum cover. So before we were talking about the spacing between bars, now we're talking about kind of durability requirements, aka do we have enough cover to the outside of the transverse bars or the stirrups for durability. Okay. So what we're doing here is our axis. Sorry, this is the axis distance that we assumed, right? And so we have to find the cover, right, through subtracting the stirrups and half the bar diameter. So if I draw a little diagram, right, you can also see it on the slide. That's your axial bar. That's your stirrup or your transverse bar. We assumed this distance here was 65. We're going to assume that the transverse bars or the stirrups are N12s. In other words, they're 12 millimeters thick. And we're gonna take half the axial bar diameter. So that's an N28. So we divide that by 2. And we want to find the clear cover. Okay, so here to here. And what we find is that is equal to 39, I believe. Okay. So give me a sec. So that's 39, which I know it says that we should have a cover greater than 40 mil, but we've made some assumptions. Like for example, we don't actually know what the stirrups are. They could be N10s. And the other thing is that 1 mil is not gonna make a huge difference. Okay, so if you think of like steel fixes and the bar placement, right, that could be plus or minus like 5 mil, right? So 1 mil at the end of the day is not gonna make a huge difference. So that's fine in the design. Okay, and so that's the final answer. So I realized it's nearly 3, and I was supposed to cover shear, but that's going to end up being pushed to the next workshop, okay? But yeah, let me know if you have any questions. You can come up the front and ask. Otherwise, you're free to go.